Okay, so we're going to work out what the uncertainty in the theoretical gradient is using the new table method we've been practicing. So I'm going to make that a bit smaller so I can get my table. So start off with my table, a little bit smaller again. Okay, so here's my variable. There's my value. There's my sigma, my absolute uncertainty, and here's my percentage uncertainty. So, if you talk, it appears on the video, by the way. So my variables are, well, pi has no uncertainty, d. Okay, so value of d, its value is 0.7 times 10 to the minus 3, but I'm going to put that in here, times 10 to the negative 3 meters. So I'm just going to stick with the 0.7. I'm going to assume that it's accurate to the significant figure it's written at, so it's somewhere between, it's somewhere bigger than 0.6 and somewhere smaller than 0.8, just for the hell of it. Okay, so 0.1. My next value is the voltage. I've got the voltage as well, voltage, and that's in volts, and that's 1.0. You've got to have your right decimal places in this, so there you go, 1.0. I'm going to say that's plus or minus 0.1 as well. And rho, okay, I can't write rho using this, I'm going to call it R, and that's in times 10 to the negative 6 ohm meters, okay, ohm meters. Okay, so there's my values. And that's 6, and I'm going to say that's plus minus 0.1 as well, just for the hell of it. So first we need to know what the percentage error is. Is that big enough to see at the back? Yes? No? I'll make this a bit bigger, and because we don't need the theory statement now, we move that over. Okay, so my percentage error equals, what's this as a percent? Well, it's going to be the value of the absolute error divided by the actual value multiplied by 100. Yeah, and we don't want that many, we only want 2 significant figures, so let's roll that down to 14, and remember that's as a percent. Okay, V, so again it's equal to that out of that, to make it a decimal, times 100 to make it a percent. 10% inaccurate. And the same process, the percentage uncertainty in R is equaling that out of that times 100. And take that down to 2 significant figures as well. Right, so the first thing I've got to work out, looking at here is d squared. I've got a squared. So I've got to do d squared. Okay, d squared. So what is d squared? Equaling that value squared. Okay, 0.7 squared is 0.49. Yeah, that makes sense. Because I squared it, my percentage error doubles. Yes, remember, when you take to the power of, so it's d to the power of 2, the percentage error is transformed by multiplying by the power, which is 2. So it's equaling to that percentage error times 2. Take that down to 2 significant figures. Okay. Now, looking at my formula, it's going to be d squared, so it's pi d squared times v over 4 rho. Okay, so there's no more transformations. The d squared percentage error has been doubled. It's going to be times by v, that's add percentage error, divided by rho, that's add the percentage error. Agreed? And if I go to my I, and I zoom over to my practice report data and copy from here my value of I, which we worked out in theory was how much? 0.063. Yeah, 0.063. 0.063. There's my value of I. I worked it out previously. Pi times d squared times v over 4 rho. That's what that comes to. Okay? my percentage error, so let's add the percentage errors, equals the percentage error in D squared, that, plus the percentage error in V, which is that, plus the percentage error in rho, which is that. Add them all together, 40%. So I need to find out 40% of that value. So it equals 40 out of 100 to make it a decimal times this value. Is that much? Now I need to round that up. Okay, so it's 0.063 is my value, and this goes to 0.03 because I round it up. And absolute uncertainties always get rounded up. So my final answer, my I final is, we didn't bother with that calculation, we did it previously, is 0.063 amps. We calculated it the other day when you were away. If you look on the model answers, I did the calculation. It's pi times d squared times v over 4 rho. Okay, if you really want, I suppose I could do it again, but we did the calculation last time.
So why is d squared not 28?
D squared.
On the far right, d squared. Go down. Then down 3. Down 3. Yeah, across 2.
Because it rounds up. Two significant figures.
Like 14.2 something?
Okay, this one here, this is why, worth asking Adam, this was actually 14.3.
Okay.
Yeah, I went to two significant figures with no rounding. But the computer, even though I'm only displaying two significant figures, carries 9 or 10 decimal places. Yeah, so it's this whole rounding until the very end. We just don't bother with anymore. Okay?
Yeah.
Good call. Nice one. And so even if you in the NZQA model answers for 3.1, I'm not kidding, they had that, which is so horrendously horrible and stupid and shows you don't understand what an uncertainty is. Yeah, even for the final value.
That's uncertain, is it? That's pretty certain.
Exactly, it's pretty certainly uncertain. It shows a complete lack of understanding, but that's what's in the model answers. I've written to the moderator and he says we don't assess on that anymore. I agree. So anyway, we're not going to do that. We're going to display things correctly, but I'm not going to mark you down if you don't. Oh, wrong one. Sorry. I'm not going to mark you down if you show that, but I'd like you to show two significant figures. Okay? And even at this end, yeah, even if you put 0.063 plus or minus 0.0254 like that, even if you did this, and this had lots more decimals, even if you left it as that, I still give you full credit. But it's nonsensical. Unbelievable, I know!
No, I'm talking about Rubens.
Oh, no, I believe in Reuben.
No, yeah, you wouldn't.
Okay, happy now? Any questions? No.